welcome everyone to today's CHBA Net Zero webinar. I wanted to start with a few housekeeping slides. First, an introduction of myself. I'm Sonia Winkleman, Senior Director of Net Zero Energy Housing at the Canadian Home Builders Association. I will be the host for today. And we also have a growing team over here at the Net Zero Council staff over at the CHBA. And if you do need ever get a hold of us, you'll be able to access our contact information in the slide deck after the webinar. So before we get started, I wanted to touch on some housekeeping items. First, the webinar is being recorded and CHBA members will be able to access not only the webinar recording, but also Steve's slide deck at chba.ca/nzwebinars. You will be in listen-only mode. Sorry, I've been talking too much today for the duration of the webinar. But we do have the questions section of the dashboard available for you to type your questions in throughout the course of the webinar. We will take questions at the end after Steve's presentation, so please do feel free to put them in at your leisure, and I will relay those questions at the end. And of course, you can also change your screen view. There's like a sliding slider you can use in between, also on the view icon. That'll help you change how you're seeing between the presentation as well as the individual webcams as well. So feel free to make that customized to whatever you are comfortable with. I also wanted to thank our gold sponsor, Owens Corning. They've been a big supporter of our Net Zero Council from the start of our council back in 2014 and have been wonderful partners for us as we've been working on net zero. So feel free to contact them at owenscorning.ca, or also, again, you can contact Sal or Lewis directly as well. I'd also like to thank, of course, our Net Zero Council Silver and Bronze sponsors. Without all of our sponsors, we wouldn't be able to do the fine work that we do. And so we're really happy that all of these great companies are on board with our projects and our initiatives. So we've got some dates coming up for some new webinars. In June, we've got a webinar coming up with Panasonic, July, AeroBarrier Canada, in September, Enbridge Gas Distribution, in November, Fortis BC, and in December, Reliance Home Comfort. So you can always get up-to-date information on the webinars as they get posted at chba.ca/nzwebinars, and you'll also be able to find the registration links there as they become available. So before we get started, we do have some polls I want to run. The first question we're going to be asking is, who is here? So I'm just going to launch this webinar. We basically just want to get a sense for whether you're a builder, developer, renovator, trade contractor, supplier, manufacturer, and then that way Steve will have a better idea too, just in terms of who's listening in today. I'm going to give everyone a few more minutes. We've only got about 50% participation in the poll, so we want to get a good sense for who's here. So we just need a few more folks to participate, and then I'll close this poll off. Great. All right, just 8% here. So I'm going to end this poll and share the results. So it looks like the majority of participants are indeed builders. And then the next is our professional services folks. So likely a lot of energy advisors. And then we do have a few developer renovators and a few others, manufacturers, local HBA staff. So that's great. Wonderful. Thank you so much for answering that poll. Our next poll that we're going to run is just to find out where you are from. So where in Canada are you coming to us from? A lot of times we see heavy Ontario, BC, Alberta participation, but it does look like we've got some good Saskatchewan, Manitoba, and also from the East Coast as well. Let's see, we've got 85% participation on this poll, so I'm going to end that and share the results. Okay, it looks like, again, we've got 31% of you are from Ontario, 28% from BC, so almost a tie there. Then about shared equal from Alberta, Saskatchewan, some Manitoba and Newfoundland, and then a little bit from Quebec as well. Wonderful, thank you so much for that. And now what we're gonna do is we've got two polls that Steve would like to know a little bit more about, whether or not you've used a heat pump in the past, a residential heat pump. So if you have used them, that's great. We want to know if you haven't, but if you are interested in exploring it and you haven't yet, there's also an option for you to choose that as a response as well. So I think we've got a full response on that. We'll end the poll and share the results. It looks like a good chunk of you, so 60% have used a heat pump in the past. That's great. About 18% of you are still exploring it and you haven't done it yet. And then 23% have just said, nope, we haven't tried it. We've got one last poll we're going to do, and that is for those of you who have not yet used a heat pump. What is the reason? Is there a specific reason you haven't tried it yet? So we've got cost, concerns about low ambient temperature, reliability, aesthetics, / looks, power consumption, or is there another reason why you have not yet tried a heat pump? All right, so I'm just going to wait for that to slow down. It looks like we've got some good participation in this as well. Okay, and I'm going to end this poll and share the results. So it looks like we've got 39% have said cost is a concern, 26% about the low ambient temperature. The next biggest one is an other. So feel free to put that into the question section of the dashboard if you feel like sharing that. And then we've got a few folks also saying the aesthetics or the power consumption might be a concern. Wonderful. Okay, well, thank you so much for participating in those polls. So now I want to go ahead and introduce Steve, our speaker today. So obviously the title of the session is Heat Pumps, a More Efficient and Healthier Solution. So Steve is the Residential Products Business Development Manager over at Mitsubishi Electric Sales Canada. He's going to talk about some impressive advancements that we've seen in recent years to the building envelope as we strive for greater energy efficiency. But a lot of builders have not yet made big changes to the mechanical systems that they're installing as those envelopes increase in performance. So point in case is that the most used thermal appliance is a coefficiency performance of less than 1. So he's going to give you some more details about the performance of heat pumps. And in this webinar, we're also going to explore, of course, the efficiency gains that the heat pumps provide, as well as the air quality, comfort, benefits for the occupants. You'll also learn about pairing a hydronic coil and heat pump air handler to run off the water heater, which allows a dwelling to reduce the amount of fossil fuel appliances and thus, of course, the carbon footprint. So really excited to see Steve's presentation. He's also brought a guest builder with him that's going to chime in towards the end of his presentation. So we're looking forward to that. So I think, Steve, I'm going to stop sharing my screen. So feel free to bring yours up, and then I think we're good to go.
Mm-hmm. Give me 1 second here. Sorry, folks.
Did it disappear on?
Okay. There we go. Okay, I think we got it.
Got it. All right, great. Take it away.
Okay. Good afternoon. Welcome. As Sonia has mentioned, my name is Steve Cornelius. I work for Mitsubishi Electric Canada, and we're going to be discussing heat pumps, the ins and outs of them, and how they're going to be a good choice for a lot of the builds that you people are doing. So this is what many of you think our future looks like, but I can assure you it's not going to be that bad. Today, I'm going to cover, who we are, history of the heat pumps, energy efficiency, greenhouse gas emissions, products and features, applications of some of these systems, and we'll go over just a couple of projects. Mitsubishi Electric Canada, we have a vision to be an industry leader in providing innovative heating and cooling and ventilation technology engineered specifically for the Canadian climate. And that's because we are based here. Things that we do are for the Canadian market. We operate separately than the rest of our divisions. And our mission is to deliver quality, comfort, and value to all Canadians through leading edge engineering, locally inspired design, and a dedication to superior service. And so anyone who has dealt with us knows that our customer service is second to none. If you have a challenge and you look for technical support, we're there to back you up. Now, just before we get into the where's and whys of heat pump, if many of you who aren't in BC, I don't know if you know, but as of April 1st, the province of British Columbia dropped the PST on heat pumps, so the purchase of all heat pumps. And then on top of that, they increased the PST on fossil fuel systems. So BC is definitely leading the charge in energy efficiency and reducing the greenhouse gases. And hopefully the other provinces will follow in their footsteps. Sometimes you hear it's called MESCA, which stands for Mitsubishi Electric Services Canada. We were established here in 1979. And we're highly involved in sustainable initiatives with many organizations, obviously CHBA, Net Zero, CAGBC, Active House Canada, Passive Buildings Canada, Enerquality, TRCA, NRCan, and anybody else who's looking to do sustainable initiatives. For some reason, it's not advancing. There we go. Okay, sorry. So heat pumps, where do they come from? And why has my cousin heard of them? So heat pump technology is not new. People like to think of these as these new, technologically advanced, newfangled things, but the basis of heat pumps were created over 150 years ago. And then the first mini split was introduced 54 years ago. So Mr. Peter von Rittinger built a vapor compression system to remove salt from water. And that was the first iteration, which obviously led to the refrigeration cycle. And then in 1940, Mr. Robert Weber developed the first ground source heat pump by modifying his refrigerator. Seems to be a delay when I advance. There we go. So as we all know, technology is ever evolving. The flat screens that we have in our homes right now came from a massive box with a tube in it that usually weighed a couple hundred pounds. That was first available in 1939. So it goes without saying that heat pumps have gone through a tremendous transformation since the first introduction back in the late 60s. So in the last couple of decades, Mitsubishi Electric Canada has pushed for the cold weather performance. And Canada now has systems that can deliver heat at our winter design temperatures. And we'll get into those low ambient temperatures further on. So what is energy efficiency? So in the most simplest definition, it's using less energy than something else to get the same task done. So when you're talking about heat pumps, we're comparing them to other forms of heating and cooling, obviously. So many things in our lives use more energy than they need to. And so a simple example is the incandescent light bulb. It wasted a lot of energy. Only 5% of the energy that it used created light. 95% was heat. And now we have LED light bulbs that are 90% efficient. And our trusted cars, grossly inefficient. They started off at 15 to 20% efficiency, and now we're only at 20 to 30%. And so that's looking at the fuel that goes in, only 20 to 30% of that fuel is being used to move the car. The rest of it is creates heat, or it's wasted in heat, sorry. Now, I wasn't taught this in class, but anyway, natural gas is made up of 4 gases: methane, butane, ethane, and propane. So propane is obviously refined from natural gas, and that's what makes it more expensive. Propane is more energy dense than natural gas, and therefore more energy efficient. But you have a finite amount of efficiency that you can get from a combustion system. And so 100% would be the ultimate, but I don't think you could ever get that. There's always going to be some form of heat, but they are as efficient as they can be at this point in time. And then you get to heat pump technology. And so because a heat pump doesn't use energy to create heat, it's the closest thing we have to creating energy that there is. And so we all remember from our grade 12 physics class that you can either create or destroy energy. And so we'll talk about how a system can be 300 to 500% efficient. What is a heat pump? So a heat pump is an appliance that transfers heat energy from one place to another. It's really that simple, and it does it through refrigerant. So the vapor compression cycle is what Peter von Rittinger discovered, and that obviously later spawned the refrigeration cycle. And so this is the same cycle that's used in your refrigerator, freezer, or air conditioner. So refrigerant has a low boiling point. And so to boil a fluid, you need heat. So when the refrigerant travels through the refrigerator, goes into the coil in the box. It absorbs heat from inside that box and then it discharges it outside the box. And your freezer obviously does the same thing, except it removes more heat from the space. And it's really that simple of a concept of how a heat pump system works. It removes heat from one space and transfers it to the other space. So there's heat in the air until absolute zero, which is at negative 273 Fahrenheit. And so that's how, even if we think of negative 10 outside, there's no heat outside. There is still heat in that air until absolute zero, where everything stops moving, all molecules, and obviously we can never get to that. So to further this point, when we think of refrigerators, we think, it's creating cold, but we cannot create cold. Humans haven't discovered how to create cold. All we can do is remove heat. And so that is what the refrigeration cycle does. This schematic here is a drawing of a heat pump system. So you have your two coils. One we'll call the condenser, one we'll call the evaporator, but that's exchangeable depending on what it's doing. The compressor pressurizes the refrigerant from a low pressure vapor to a high pressure superheated vapor. It then passes through the condenser, which condenses it, and then it gives off its heat. So it becomes a cooled liquid. Then it goes through the expansion valve, where the pressure is abruptly dropped, causing flash evaporation. This process absorbs heat from the air that's going around it. And you can see this in when you have your propane tank on a barbecue. And so when you open it up, it's got a massive reduction in pressure. And of course, then it absorbs the heat from the air surrounding it. And that's why you feel it to be cold on the outside. What makes heat pumps the champ is their ability to vary their capacity and ability to reverse their cycle. And then what makes a heat pump so much more efficient than other appliances is that the refrigerant is doing all the work. The electricity that it consumes simply runs the compressor and the fans. So we have a term called COP, which is the coefficiency of performance. And this is how we get to the 300 and 500% efficiency. So you have 1 kilowatt of electric energy going into the system, but then the system's able to capture 4 kilowatts of heat from outside. And then, when you transfer that energy inside, now you have a 5 kilowatt of heat on the inside. And so this is your COP. It's just a ratio of energy in to energy out. And again, because you're not creating this energy, as the systems get more efficient, as we figure out how to use the pressure cycle better, maybe better refrigerants, we can get to lower ambient temperatures and be able to capture more heat to provide inside. Now, when we look at the operation of a heat pump, unlike conventional system, which cycle on and off, the system detects changes in the room temperature because it has two-way communication. And so it readjusts the compressor speed to provide the appropriate level of heating or cooling as required. So it's going to ramp up the speed and then hit that set point and then try to cruise at that set point, thus reducing the energy. So this is a much better visualization of what we're talking about here. So you have the green car and the gray car. And which one would you rather be on? Depends if you're a thrill seeker. But the green car represents the heat pump system versus the gray car representing a traditional furnace. So again, it's going to get up into the zone, the set point for whatever the space is, and then it's going to stay within that set point. Whereas a conventional system is going to give you all its heat or all its cooling, hit that set point, turn itself off. And then it's going to wait till it drops to, it's 2.5 degrees or whatever that set point differential is, and then it'll kick back on and kick off. And so in a really leaky home, you're going to feel, hot then cold and hot then cold, and or, the other way around in the summertime. But when you're using a heat pump system, it's going to give you continuous air, and it's going to moderate that air temperature to give you the level of comfort that heat pumps are known for. Now, in a residential home, we're not going to be using 20 tons of anything, but this is just to show that there's no more efficient way of transporting thermal energy than through refrigerant. So looking at the equivalent amount of thermal energy, if you run it through a duct with air, you're going to have to use a 36-inch diameter duct. If you run water, then you get down to a 2.5-inch pipe. And then as you can see with refrigerant, it's the smallest pipe. So you can move more thermal energy more efficiently with refrigerant. And so you can imagine in a home, if you abandoned forced air, moving that through the house, you can get rid of a lot of ductwork and bulkheads. And so you can have a lot of space savings. Now, I wanted to bring this up because this is something that's it's a very big deal. This was just released by NRCan, assessing cost effectiveness of energy savings and greenhouse gas emissions. And so what NRCan did was they compared the operating costs of natural gas, oil furnaces, electric furnaces, and heat pumps across their archetype homes to see what the actual operating costs were in comparison to each other. And it was a pleasant surprise for the results. You know, I'm sure most of you have heard or have been told that running a heat pump is considerably more expensive. You know, it's running on electricity. You know, gas is obviously cheap by its rates currently, but it ends up that if you run a heat pump system and remove gas service, you could actually, a homeowner could actually have a lower operating cost. So this chart here illustrates the savings of cold climate heat pumps versus gas, where you eliminate the gas service altogether. And you know, with a home, you always have to have an electrical service, but if the homeowner can reduce one of their monthly bills and still supply the heating or the thermal comfort that they need, wouldn't that make sense? So these are charts from the report itself. The column on the left now is what people pay in fixed gas charges. So again, just imagine removing that bill from your plethora of bills. You know, that's the sort of money you're saving just on the fixed gas charges, not talking about usage. And then the column on the right shows the cost difference if you keep both services. So say you kept gas in the home to run the hot water tank, or you know, maybe the barbecue or whatever. So it's still over a course of a year, you know, you're looking at maybe a couple $100 in most of our communities. And finally, this one is the operational cost savings over an oil furnace. So that's obviously a no-brainer. So I was speaking with a man with great knowledge a few weeks ago. He happens to go by the name of Gord Cook. And he said that we have to stop talking about return on investment, ROI, when it comes to energy efficiency. Every day people buy energy efficient appliances and, you know, you'll get this new fridge because it's more efficient than the last fridge. But what's the ROI on that? You know, if you buy a new car with a turbo engine, it's going to use less gas than the V8 that you may have had before. But are you calculating the ROI on that new car, the purchase of that new car versus the old car? So why do we do that with our heating and cooling systems? So now we'll get into talk about carbon, greenhouse gases, and indoor air quality. So my thoughts and many people in the industry is that indoor air quality should be a very important feature in the purchase of a new home. With all the respiratory illnesses that are out there, you know, especially with children with asthma being the most common, shouldn't this be a primary concern? Now, ASHRAE 62.1 deals with ventilation for acceptable indoor air quality. But what about the off-gassing materials in the home? Is that something that some of the builders are looking into? And what about gas appliances releasing toxins in the home? Is anybody aware that this is a thing? There was a recent article in the CBC that states that gas stoves produce more indoor air pollutants than anyone ever expected. And this follows a concerning study published by a professor of Stanford earlier this year, Rob Jackson. It stated that the gas stoves leaked unexpectedly high levels of methane, even when they were off. And on top of methane, they also, from burning natural gas, you got nitrogen oxide, formaldehyde, nitric oxide, and carbon dioxide, carbon monoxide. And so these are articles that you can look up right now. They're currently still in circulation. There we go. So most modern furnaces and hot water tanks are sealed combustion. And they're exhausting to the outside. So that's not really a concern as far as leakage, but there's still natural draft units out there. So those would obviously be a problem. And then, your gas stoves are obviously exhausting into the space, maybe some gas fireplaces. And these are key selling features in our modern homes. But you really can't speak to wellness or a healthy home with a stove burning and exhausting gas in the living space. There's no hood in the world that's going to catch all the toxins. In 2015, Health Canada issued new residential air quality guidelines, but somehow gas stoves were never included, and they are the worst offenders. Now, obviously, with heat pumps, there's no combustion to be concerned with. They also have a higher airflow rate, which allows for more air movement and possibly better filtration. Now, I think we're all aware that buildings are the largest source of emissions through the way we heat our spaces. And this is one of the main impetuses for moving over to heat pump technology. And then we've got the carbon pricing, which has already started. The price is going to increase $15 per ton per year up to $170 by 2030. So that's only 8 years away. So this will double the consumer cost of natural gas. So this is, when you're looking at something like this and talking to potential homeowners, this is something that really should be looked at because their cost of ownership is going to increase if they're still primarily on fossil fuels. So now we'll talk a little bit about the product. So with our systems, we guarantee 100% of our heating output at -15. This is for all our cold climate systems, and in some of our new products, we're getting even lower. We guarantee 80% of our heating output at -25. And then with our Zuba systems, they're still at a COP above 1 at -30. So still more energy efficient than a fossil fuel system. Now, obviously, in the Canadian climate, when we're looking at the output of systems, any system is going to have to work harder as it gets colder. So this chart here illustrates, again, that 100% heating, maintaining that to a certain point, and then the degradation of performance compared to other systems on the market. They tend to lose their heating capacity a lot sooner. So what some systems will do, or what some firms will do, is actually use a larger system, but still call it a smaller system. So take a 3 ton, but call it a 2.5 ton so that they can get more performance out of it. And then when we talk about temperature, so, it was -30 last night. In Toronto, it doesn't hit -30. We're used to talking about the wind chill, but that's not a factor when it comes to these systems. And so this chart here is a temperature curve for Ottawa for 2020, and looking at the average temperatures. And so it very rarely hits those low ambient temperatures in the majority of our living, or a majority of our population. So, for 90% of the population, the cold climate systems are actually able to supply enough heat to keep a home thermally comfortable. So this is one of those new products that is out actually right now, where now the 100% capacity is down to -20. The other features are relatively common to our other products, but again, this is where we're trying to do is create more capacity at lower temperatures. We're hoping shortly to have 100% capacity at -30. and then there really wouldn't be any worry for, again, the majority of the population. But we have systems that are up in northern Alberta, up in Yukon, which work obviously as a hybrid with maybe an electric coil, and we'll talk about a hydronic coil later. And it's still efficient because the majority of the time it can still operate to satisfy the thermal load for that space. And then it's only in the extreme conditions that you'd go to the secondary source. So some wall-mounted units, FH, which is our top seller, the GL. Obviously, wall-hung units are not something that a lot of people want in their modern homes, but they definitely work for attic spaces, cottages, places where people just don't mind having a big white box on the wall. This is the GS. This will be coming up shortly, where it'll have 100% at -15. So it'll be an upgrade from the GL. The SLZ, which is a 4-way cassette, you don't often see that in residential applications, probably more in a light commercial. But the MLZ is something that not a lot of people know about, but it's a great option for indoor space where it's going to sit between 69 center joists. And so maybe in a multi-split system, you could have one of these in most of the rooms, also all going back to the outdoor condenser. And then, of course, it fits into the ceiling, so it's got a nice aesthetic look. And then we have the slim ducted unit on the left, and then the multi-position air handler. So usually when someone's talking about a Zuba, they're talking about the multi-position air handler. But that does cover all of our cold climate systems, but this is something that you could integrate into a centrally ducted home, depending on the side of the ductwork, but it could replace a fossil fuel furnace or electric furnace, and it has in many, many cases. And then last but not least, the floor mounted unit. Ideally, this would replace a radiator on a wall, that sort of space, or maybe a PTAC. And again, depending on people's preference, it could work in a modern space, but this is something that would be more on the floor. And then here we're looking at connectivity, the various options that you have. Obviously, one-to-one systems, multi-split systems, standard and cold climate. And as I mentioned, Zuba, these are the various Zuba brands: Zuba Central, Zuba Multi, Zuba Single, and Zuba Single Plus. Now let's get into the applications of some of these systems. So whether it be for an apartment, a townhouse, or a detached home, a central air handling unit would take the place of a conventional furnace and provide conditioned air through the centrally ducted system. And of course, it comes in various sizes, and you want to make sure that you've done a thermal load calculation for the space to size the system appropriately. Typically, furnaces have always been oversized, but with heat pump systems, if you size it correctly, you can definitely have a smaller system that obviously is going to use less energy and just be more efficient for the space. And then when you're designing or building a home with multiple levels, a multiple split system is obviously a wise choice for occupancy comfort. With a central system and a single thermostat, how are you supposed to satisfy the temperature requirements for levels 1 and level 3 at the same time? With a multi-split system, each indoor unit is independently controlled. So you can set up your HVAC system to have anywhere from 2 to 8 zones. So I actually was on a talk where a builder was talking about doing this instead of running ductwork, and talking about the space savings that there was running refrigerant lines versus having bulkheads all throughout the house. But again, in an ideal world, a multi-split system allows you to zone a house, which is the ultimate, because if that bedroom, if that person wants it a little bit cooler, they can have a little bit cooler, and that room it can be a little bit warmer. And then obviously, depending on the orientation of the house, maybe one side's getting the western setting sun, So it's still warm, but then the other side of the house is cooler. So the concept of zoning, using dampers is one way of doing it, but it's obviously not the same as if you had full temperature control over the space. This is an image of the MLZ mounted in the ceiling. Right here. And then I'm not sure why this is bowed like that. That's obviously not the way it's supposed to look. But again, mounted in between the joists. That's how that works. And the floor mounted. And then now let's look at the installation. So based on the weight of the condensers, you can put them almost anywhere. They can be on the roof, they can be on balconies, they can be on a wall, they can be near a window, they could be on grade. Due to their quiet running sound levels, you can have this near a window and not worry about the sound. You're talking about 50 to 55 dBs. A lot of times with these running, you have to look at it to see that it's running. So there's no noise challenges. And obviously you're not worried about venting challenges either. So you can place them close to doors, wherever it makes sense. And they only need about 6 inches behind them for their intake. And then they need about 3 feet in front of them. So if you have two buildings that are very close to each other, again, you only need 3 feet in front of the unit for it to function properly. Now we're going to get into the hot water coil. So for many people that are very hesitant to get rid of gas, you can hedge your bets by going with a hybrid system. This is something that's been going on for quite some time. I have a builder up in Ottawa who all his homes are built this way, with these sort of systems. And so it's to put a hydronic coil on the top of an air handler, and then you can heat that water any way you see fit. So whether it be by an instantaneous boiler, a tank, even a wood-fed boiler, it doesn't matter. But that gives you the ability to supplement the heat, especially if you go with a standard unit. Then you have the ability to use the heat pump for the milder seasons. And then when it gets down to the winter temperatures, you can kick in the hydronic coil, and that will cover you off for the temperatures that the system can't satisfy. This here is a diagram of a case coil from direct coil that is pretty common for the builder that I just mentioned. Obviously, you size the coil based on the airflow and the water flow going through it. It needs to be paired with a pump. So with your instantaneous boilers, some of them have pumps built in, so then that can run the whole system. Sometimes you have to add a pump. But either way, the heat pump system has the ability to signal when to kick in the pump to run the coil, so that you get that secondary system going. And here's just some performance stats. This particular coil with 875 CFM will give you 44,000 BTU. And this schematic here is just showing the logic sequence for turning on and off whatever that secondary source is. And so again, that's all integrated into the board. Just a simple connection in our logic board, which will send a signal out to whatever that secondary system is to kick in when the set temperature is not met after a certain degree temp. Now we'll look at some projects. And first I'll start with one that I'm sure many of you know, but this is by far the most impressive net zero development in Canada. So this is the Sifton West 5 project, which is a 70-acre site in London, fully sustainable mixed-use development, where they house their headquarters. They have senior living, and they have townhouses for rent. And they have 75 units in each phase, and they're going into phase 3, and they have a waiting list for these units. So these systems all have multi-position air handlers. The condensers are, I believe, 1.5 to 2 tons. Obviously, being net zero spaces, they're highly thermally insulated. So they've had these now, and I think they started about 3 years ago, and have been singing the praises of these homes and these systems ever since. And now I'd like to bring in a good friend of mine, Michael Broom, to speak about his project. Michael, are you there?
Yes, I am. Can you hear me?
Yes.
Okay, good. Hello, everyone. Sorry, I closed the blinds and the doors because there's a lot of sunlight coming in on my monitor. Yeah, this is a project. I did the passive house training. I did R2000. I did net zero. I went to the conference in BC just before COVID, and everything I was told there, I've now built one, and it's all true. This is a semi-detached project built on a corner lot in Ottawa. I have to say the units are performing better than I ever anticipated. I had a lot of consultants on this because it's the first time I've done a full net zero project, and I want to make sure that we got it right. My first heat pump experience was in 1975, air source, and let's just say it wasn't pretty. It functioned, but barely. Obviously, technology has increased dramatically since that time. And one of the things I learned at the conference in BC was that Mitsubishi makes the best product on the market. So I thought, I'm going to start this. I'm going to start at the top. I want to see how they perform, and I now have a yardstick to measure by. And as they also told us at the conference, you're not selling a building product, you're selling a lifestyle. And the big part of that lifestyle is being able to walk through your house, breathing clean air. You don't hear a furnace going on. You don't have drafts. You don't have high temperatures. You don't have low temperatures. In fact, I go to friends' houses now, and I stayed overnight recently, and I thought the water was running all night because the furnace kept coming on. And I just wasn't used to that sound anymore. So yeah, I'm very happy with the units. Something else that's come up a couple of times is I'm showing the units to people, and they go, well, this is not a very quiet system. I can hear it running. I said, no, that's the neighbors 2 doors down. That's their system, not mine. You can actually stand, as Steve says, you can stand beside these units. I have them on small patios in the backyard. My concern was that the noise would be too loud, and you don't hear anything, as he says. Sometimes you have to look at them to make sure that they're running. So overall, very happy with the product and the installation. We did go with an electric backup heater for code. I didn't use the hydronic, even though I do have gas in these houses. There's 6 inches of insulation under the basement floor, 5-inch slab with hydronic heating in the slab. So we have an on-demand combi boiler in the basement. It basically heats the basement space and provides domestic hot water. I didn't go electric because the only one I could find that met the demands I was looking for was a 3-phase power system, and it's a little too expensive for single-family homes. So we can actually, I don't think the electric heat will ever come on, the backup electric, because what I do is I open the basement, this open stairwell to the basement. There's one door into a room. I open that door, and the heat rising from the basement generally makes up a difference if it's very cold. I'm living in the unit on the left right now. I'm torture testing it over the winter at -30. I turn the system off just to see how long the house would take to get cold. One thing you will notice is if you need a sudden increase in temperature, you won't have it. It's a gradual climb, and when it gets there, it stays there. So if, say, I had to increase the temperature 5 degrees for whatever reason, the electric backup would probably be providing that heat. But other than that, no, the system works very well. It was -31, -29 one day in Ottawa. And I went outside and the units were running. So I know the -30 cutoff works. Okay, so I'm available for any questions if anybody has any.
Sonia, do we have any questions in the chat?
Thanks so much, Michael and Steve, for the great presentation, Steve, and the great commentary, Michael. That's wonderful to hear. We have a few questions that have come up. I'm going to start with the first one here from an anonymous attendee asking if we could share the hyperlink to that NRCan report. I did go to the LEAP webpage, and I don't think it's posted yet because it's brand new, correct?
Well, it's not on the LEAP web page. It's through NRCan. Like that link, if you copy it, or if I would say when I share with anybody, it takes you right to the NRCan website, and you can download it.
Perfect. So then that's what we'll do is for the anonymous person, when you go to our webpage and find the slide deck, you can just click on that hyperlink that Steve has put right into the PDF or into the PowerPoint. So that link is there. Wonderful. Great. Thank you so much, Steve. The next two questions are actually related. They're both in regards to getting to those lower temperatures. So someone is asking, how about -30 degrees? And the second person is asking, they're saying it's an R&D question. What is the outlook for heat pumps with a COP of 1 at colder temperatures? For example, -35, -40 is sooner years away. I know you already addressed a little bit of that, but I don't know if there is any work in progress still to continue for going to those even colder temperatures.
Right. -40, I don't know how many years away that is. That's a big jump. Right now, the Zubas, I think we have the cutout at -32.5. The next iteration is going to be probably about -35. That's what we've been told. That'll be the cutout. And again, trying to keep that 100% capacity or get it lower. So the next step would be 100% at -25. But the thing is, when you say just an electric coil as a backup heat, again, it's only going to be operating for a very small percentage. If you look at the whole heating season, it's going to be a very small percent of the time that it actually has to kick in and do that work, because you don't often have daytime highs of -35. Obviously, in the extreme north, that could be more the case, but it's still going to be more economical to have a heat pump system than a fuel system. Obviously they have access to oil up there, and that's usually what they're using. So it's going to be better than that. So when you look at the operating range of the heat pump, it's going to be operating at a very high efficiency, and then for a very short period of time, you may have to kick over to straight electric or whatever that backup system is, but it's still going to be more efficient than the previous system.
Great, wonderful, thank you. And then we've got another person asking, are heat pumps controllable by smart homes for remote control?
So heat pump systems like to use their own controls because there's two-way communication there versus a standard thermostat that only has one-way communication. But we do have an interface that will allow it to talk to an Ecobee or a Nest or any of those systems. And then now, if you're going into a MERB or a bigger complex, there is central control that you can control all the systems through MNet, which is a communication protocol. And then we also have a controls system called RMI, remote monitoring interface.
Great. Okay, so there's definitely options.
Definitely options.
Wonderful. Okay. Lou is asking or says, this all sounds great, but how are builders dealing with indoor air? Are they installing ductwork and HRVs? So what are the ducted options where you could tie into the heat or energy recovery ventilators, perhaps?
Right. So if you're doing a centrally ducted system, so a vertical air handler running through ductwork, you can still tie in your ERVs or HRVs into that system. And so you can tie in the controls as well so that they'll operate collaboratively. So there's no issues there. Now, when you're going to a multi-split system, then obviously you're not having the ductwork. You're going to have more, probably smaller fresh air systems in the various spaces to get that fresh air in. But if you're doing a centrally ducted system, then there's no real difference. You're still going to pipe it in the way you would have before, and then you can integrate the controls.
Exactly. Wonderful. Okay, as another anonymous attendee is asking, what is the ability for units to recover after a power outage if temperatures are very cold and no backup heat is installed? I guess the one comment I'd say there is in our program, at least with net zero, there is always the secondary heating system required. I believe that's a building code thing too, is it not, Steve?
Yeah, right now, because the way the code is written, they consider heat pumps electric systems, so they have to have a backup.
So
But
there's no worry about
regarding,
it because the backup system would always kick in, right?
but if we're talking about a power outage, then you're out of power, so nothing's working.
Oh, sorry.
Power
Yeah.
power outage, your furnace goes out, everybody, there's no heat, period, unless you got a gas or a wood fireplace.
Yeah.
So recovery time, it's going to run full speed to try to hit that temperature as soon as it can. Obviously, it wouldn't be as quick as a fire burning system, but it will run full speed to get to it's back to its set point.
Yeah, because even if you've got just a regular furnace with the power outage, that means that the fan is not even going to operate, even if you have a gas-based fuel system.
That is correct.
Right. Awesome. Okay. Peter is asking, which system is more efficient, a ground or air source heat pump, and how is price a factor?
Right. So a ground-based system has some higher efficiencies. And because it's not dealing with the extreme temperatures, you have a constant temperature in the ground of around 10 degrees Celsius. Then obviously in the colder climates, it can do a better job. So it's going to be more efficient overall. But then you got a cost premium of probably 30 to 40% because you have to do boreholes unless you can go horizontal.
My understanding too is that with these net zero homes, because they require such low thermal loads, that the air source heat pumps make more sense. But if you've got larger buildings with both heating and cooling needs that are balanced, like I keep hearing things like if you've got a community center with a skating rink and a swimming pool, that's an ideal situation for a ground source heat pump because you've got that balanced need for both heating and cooling in a larger space. So that would make more sense than say a single family net zero home on its own where the loads just aren't that high.
Mm-hmm. Yeah.
Okay.
Ground source is again great, and if you have the space, the real estate to do the boreholes and whatnot, it's a great option. With VRF though, you can tie in VRF to ground source. So now we're talking about commercial central systems, and then they can also do heat recovery. So in these large community centers where you have one space that's in cooling, one space is in heating, they can take the heat from one space and transfer it to the other space. So VRF systems are fantastic for commercial institutional spaces because they have that heat recovery ability.
Right, fantastic. Great, thanks, Steve. Stuff one is asking how to get fresh air in the house. So what replaces the ERV or HRV in this system? And I'm going to say it's not a replacement. This is a heating and cooling system, whereas ERV and HRV are ventilation systems. So they're two separate things. Am I correct in that, Steve?
That is correct. Just like your furnace isn't a fresh air system, a heat pump isn't a fresh air system. A fresh air system is your ERV or HRV. And so it will integrate no differently. You tie it into the controls so that it turns on when the fan's on, so you can get the airflow through, or you can have it be independent and have its own ductwork. But it's a fresh air system, so it is a different system.
Okay, perfect. Thank you. Stefan is asking, when will we see the EcoDan cold climate air to water heat pump with CO2 refrigerant in Canada?
Well, there's a whole bunch of complexity there. EcoDan's one thing. That's so the EcoDan, for anyone that doesn't know, is our air to water system. So it's a hydro box that connects to the outdoor condenser, and then it does a heat exchange from the refrigerant to water so that you can do in-floor heating and possibly domestic hot water. We have this system. We had it here many, many years ago, but it was ahead of its time. We have it in Europe, but they're using R32 and we're still at 410. So when Canada makes its refrigerant change, then we can bring that product back. And then CO2, I don't think we're there yet. We're probably going to go to our 454. CO2 would be amazing, but it's very high pressures. And so The industry on a whole would need a lot of training to get up to that. It makes a big difference in the operating pressures dealing with CO2. So again, that's something I wish we could get to sooner, but it's going to take some time.
Yeah, so I understand the reason people are looking for the CO2 refrigerant is because essentially it's a way to use existing CO2 into as a replacement for the refrigerant, because the current refrigerant has a higher global warming potential than using the CO2 in its place, correct? Is that how it's operating?
That's correct. Yeah, that's why everybody's moving to a new refrigerant. We're always trying to lower our GWP. So 454, I think, is around 675. Where 410 is up in, I think it's 1500, somewhere around there. So bringing it down quite a bit. And then CO2 obviously is close to zero. So that would be the ideal. But again, the pressures that are required for CO2, right now they're using it in commercial, but residential, for whatever reason, most companies are staying away from it just right now.
Okay. But do you think that that's something that's coming down the pipe just based on the need to reduce global warming potential of products? And
oh, for sure. Okay. I think that's the end goal, getting to CO2.
Yeah. Okay, great. So we'll probably hear some more about that in the coming years then.
Right.
Great. Wonderful. So I've got a few more questions here. Robert is asking, I built a net zero ready luxury home recently, first net zero ready build, and I'm currently living in it. I have a combi unit using a heat pump, but find that it is a cold heat, if that makes sense. Has anyone else experienced this? The temp says 23 and I confirm independently, but it feels colder than that in the room. ACH was under 1.0.
So it's a cold heat.
My guess is it's like, it feels like what you said there, the ambient temperature feels different, right?
Mm-hmm. Because I mean, a heat pump can discharge air up to about 120. So I don't know if it's a humidity issue where it feels a little bit cooler, but it should be able to give you the warmth. Like there shouldn't be there shouldn't be a sacrifice in the feeling of warmth from using a heat pump system.
I actually heard recently someone recommended to me, because I'm also in a new net zero ready home, that you, with an air source heat pump, you actually have to just turn the temperature up a little bit to get that same kind of, because we're used to that blast of heat, right, from a furnace. Mm-hmm. So the way you're sensing that heat is certainly different with the air source heat pump than it would be from a typical furnace. So perhaps, like you said, that maybe there's a humidity issue there. But yeah, if you've got an ACH of under 1, it certainly shouldn't be any kind of feeling of cold coming off of the envelope of the home, right?
Right. Yeah.
Yeah. So I would suggest to Robert, maybe we can take a conversation offline if you wanted to send me an email, and then maybe we can even set up a conversation with Steve offline and see if we can't figure out maybe what's going on there.
That sounds good.
Okay, great. A few more questions here. Curtis is asking, do any of the Mitsubishi air source heat pumps provide hot water when it's running in cooling mode, i.e. similar to how some ground source heat pumps work?
Well, again, because we don't have the air to water here right now, no. Simple answer is no. But that is something I'm hoping to have in the next 24 months.
Oh, wow. Okay, in a couple of years. Great. We actually got quite a few questions here, so I know it's coming up on time, but I'm going to try and plow through a few more here. Paul is asking, any special consideration when retrofitting an air source heat pump from a current furnace setup in an existing home?
Yes. So the duct volume, very important. That has to be examined to see what your previous airflow was and what that duct was designed for versus what your new airflow is going to be, and see if there's any adjustments that have to be made there, and if you have enough air volume to satisfy that, because otherwise you won't get the air distribution that you need.
Okay, perfect. Yeah, we've heard similar conversations with our renovation working group as well. The ductwork is the distribution system is critical. An anonymous attendee has asked, has there been any any research or testing of installs in older unretrofitted houses with a minimum insulation or air barriers? A 1960s house, for instance, can they keep up with the heat loss?
Right. I had a project that I didn't put up there because I think we were talking about new builds, but with regards to retrofit, I have a house in Campbellford, which is Eastern Ontario. They happen to be a dealer, a contractor. And so they have a 1970s home that they didn't do any exterior renovations to. They had an oil furnace that heated the space. They removed that and put in a 3.5-ton Zuba system with electric coil backup. And they've been singing its praises for the past 4 years. So
Really?
it is
Without any
feasible.
envelope work?
Correct.
Wow. Okay, I have not heard yet. So that's a really great story to tell because I haven't heard that yet. So very
We
interesting.
have a case study on that one. Yeah.
Okay, yeah, maybe that's something we can post and add to your package of information when we post your website up or your webinar
Sure.
up. Great. So for those who want to stay longer, I guess a quick question. Steve, do you have a couple more minutes to try and tackle some more questions or do we need to wrap up?
Yeah. No, I'm good.
Okay, perfect. So for those who want to stay online for another couple minutes, Lou is asking, what are the options for getting this fresh air where it is not a centrally ducted system?
Right. So if it's a new build, then you can just run, 4-inch round flex to whatever spaces that it needs to be. I know Canarm has these little mini in-wall fresh air units that can be placed in various rooms. Other options, yeah, basically just smaller fresh air systems that would be distributed throughout the house.
Excellent. And then I guess he can always get in touch with you afterwards because I think you had your contact information in the slide deck.
Yes, I believe so.
Okay, wonderful. Yeah, and if not, reach out to me and I can connect the two of you. Marcello is asking, or Marcello, sorry, is what is the voltage required to run the Zuba central system, 110 or 220?
110. Oh, sorry. 220.
220 for the Zuba?
Yeah.
Okay, wonderful. Anonymous person here is asking, what is the cost comparison of gas furnace with AC versus just the heat pump system when retrofitting an existing house?
You're probably going to be, if you're looking at if you're comparing apples to apples, so high-end furnace, high SEER AC, you're probably, 15 to 20 points up for a heat pump system.
Okay. Great. Lou is asking, is there adequate supply of air source heat pumps? I've had HVAC contractors saying that there's a long lead time for Zuba.
Right. So obviously with COVID, there was a lot of challenges. And then, of course, we had the chip shortages going out throughout the world. The Ever Given that was stuck in the canal. Then we had the fires in BC. Then we had the floods in BC. So last year, by the end of the year, it became very challenging for equipment. But the logistics side of things have cleared up quite a bit. So the new shipments should be here now. And we, as a company, tend to stockpile a lot of equipment here in Canada, so we don't order it just as needed. So between our distributors and ourselves, we have quite a few warehouses where we stockpile, obviously the most common, most popular equipment. So again, this year going forward, you shouldn't find any shortages, and hopefully we can keep it flush throughout the rest of the year. Obviously, if there's as long as there's no further impedance to getting stuff here through shipping and other natural disasters and whatnot.
Yeah, I actually heard in one of our projects, it was not a Mitsubishi though, it was a different manufacturer, I believe, where they were forced to basically use a different kind of air source heat pump instead of the one they wanted just because of lack of supply. So I think that it's definitely common for a lot of the manufacturers to be having supply issues right now for all the reasons you just mentioned. So, and I don't know if other manufacturers stockpile like you do, so it's good to hear that you guys stockpile. So ideally, you'd have everything on hand for what builders are needing at this time.
Yeah, last year was an extremely difficult year for all manufacturers because there was hundreds of cargo ships stuck in ports, couldn't get to dock because of COVID and all the rest of the things. So yes, last year was definitely an anomaly, and so hopefully this year, all things being normal, things get better.
Exactly. Yeah. Fingers crossed. Okay. And now I think it looks like we're just getting into some more questions directly with Robert about his specific situation. Looks like he's got some comments there. How does air source heat pump affect humidity in the home?
It's actually pretty good because it's a less dry air because you're not using an open flame to heat the air. I know that the flame doesn't come in contact with the air, but it tends to be less dry. So on the heating side, you tend to have a higher humidity, and then on the cooling side, it dehumidifies quite well because you have a more constant airflow. So you're getting more air going across the coil, and so it's able to do a better job dehumidifying.
Yeah, and Doug Terry, I know he had done some research too on the connection between temperature and humidity. And if we have those big fluctuations in the temperatures, you're also going to see those fluctuations in the humidity. Whereas with the air source heat pumps, because they have a much more consistent temperature, that's also going to help with consistent humidity levels as well, as from what I understand from those studies. Great. Okay. And then this last comment, Marie is saying this isn't a question, it's an additional information. There was additional information from City of Ottawa pilots from the Association of Energy Engineers on air source heat pump performance with no envelope upgrades is retrofit. So it was a great webinar earlier in March 2022 to show the detailed results of performance, temperature, energy, and energy costs. Oh, that's great to know. So maybe we can somehow put a commentary on where to find that information. Maria, I'll have to get that from you afterwards, but looks like we've, well, except, sorry, Marcello is asking, where can I find a list of dealers in the GTA? I think Steve can probably put you in touch with those. So Marcello, I'll see if I can get your email address and forward that off to Steve, and he can help you out with a list.
For sure.
Fantastic. Great. Well, that's the end of our questions. Thank you so much for sticking through it. And Michael, again, thank you so much for giving your input from a builder perspective. That's always welcome. And as always, if anyone has any additional questions and you want to get a hold of Steve, please feel free to email me directly and I can put you in touch with Steve. And the webinar, as well as his slide deck, will be posted in on our website probably in the next day or so. So thanks everyone for joining us today, and enjoy the rest of your day.
Thank you everyone for attending. Hopefully I imparted you with some new information, and look forward to working with some of you in the near future.